First of all, hello and welcome to everyone. We are so glad to have you joining us here today. My name is Lauren Harrington, and I will be your host during today's webinar. Before we get started, just a few quick announcements. I know that you guys are all pros at Zoom already, so let's just zoom through this. If you have a question, use the Q&A button. It's at the bottom of your screen. Feel free to send in your questions at any point during the webinar, and don't worry because it won't interrupt the speaker when you do so. Also, if you encounter any technical difficulties with your audio, all you need to do is click on the up arrow that's next to the mute icon in the bottom left of your screen, and that will open up an audio settings menu. Chances are good that you can use those settings to fix your audio, and please note that selecting a different speaker often helps. Also, we now have automatic closed captioning available. If you would like to show the closed captioning and laugh at its mistakes, or hide the closed captioning and rid yourself of all worldly distractions, all that you need to do is click on the CC button, which is down at the bottom of your screen, and use the settings window that pops up. Finally, we would like to thank and acknowledge our sponsors, DC3 Dreams and Voice Astro. DC3 Dreams provides high-end observatory automation and web-based multi-user remote imaging. The AAVSO net observatories use DC3 Dreams ACP Expert for the Bright Star monitors and other programs. The AAVSO Photometric All Sky Survey project, also known as APAS, has used ACP Expert's AI scheduler to automatically acquire over 500,000 star fields, hands-off, at a rate of 1,000 square degrees per night. This has resulted in photometry for over 128 million objects in about 99% of the sky. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please do check out their webpage to learn more about their work. Okay, now you guys are in for a treat because the first of today's speakers is an expert teacher. An astronomy professor at Central Connecticut State University, her research focuses on the intersections between science and society, from the history of science to gender and science to science and popular culture. She has written a number of science books, including fun titles such as Particle Panic and Cosmology 101. But I imagine that many of you here in the audience know her not just for her teaching, but for her many years spent serving the AAVSO in various leadership capacities. As a council member, a president, secretary, she's done it all. And perhaps the most relevant role to mention today is the one as her current role as the leader of the solar observing section. That's because she's here today to teach us all about the most well observed and closest by variable star in the sky, our sun. Solar maximum is coming up fast and you don't want to miss it, so I suggest that you all settle in, make yourselves comfy, and get ready for an awesome talk by Dr. Kristine Larsen. Take it away, Dr. Larsen.
Thank you very much, Lauren. And I would just like to give a shout out to Frank Dempsey, who is in the audience here, who worked tirelessly on the AAVSO Solar Observing Manual, more on that later, and to my co-director, Rodney Howe. And so I'm going to now share my screen. And okay, here we go. So of all the AAVSO observing sections, and as you probably know by now, there are quite a lot, the solar section is just a little bit different because we only look at one star, the same star all the time. And we don't lose any sleep when we observe because we observe during the day. But before I launch into how to safely observe the sun, I should make sure that we're all on the same page and that we all have a basic understanding about what our sun is and why and how it's a variable star and how the AAVSO got into the business of doing daytime observing of the sun. So as I normally tell my astronomy students, the sun is quite basically just the nearest star to Earth. It's a middle of the road star. It's in the middle of its lifetime. It is clearly the largest object in our solar system. You could fit everything in the solar system inside the sun many times over and have plenty of room left over. Or if you just like Earths, you could fit 1,000,000 Earths inside the sun. I like this picture because it's kind of scary looking, because you can see this giant tongue of gas coming off the sun and a little teeny white dot representing the Earth. And it really puts everything into a bit more of a cosmic scale. And because of these huge storms that the sun has, it gives people this both misconceptions about the sun and a tremendous awe and appreciation about the sun. And when you ask people about solar activity, a lot of times what they'll say, oh, there are those flare things. The sun has those flare things. So what are solar flares? Besides giving us these beautiful pictures, thanks to all of the space probes that are monitoring the sun from well above our surface, some of them actually in orbit around the sun itself. Well, flares are very rapid explosions on the sun, and they release as much energy as about 200 nuclear weapons. So they are incredibly energetic, incredibly impressive, but they are not dangerous to the sun. The sun does these all the time, not in danger of doing anything permanently to damage our star. But people are probably more concerned about what could these flares do to damage us. And if you do a little trolling on the internet, you will find some pretty incredible headlines. You know, can a killer solar flare really destroy the Earth? A bad solar storm could cause an internet apocalypse. Solar flare warning, intense bursts of space weather can destroy life on Earth. Well, with headlines like this, it's not surprising that people have a lot of misconceptions and anxieties about solar behavior. And Hollywood is quick to notice anything that quickens the pulse of the Hollywood observing audience. If you've seen the Netflix series Into the Night, or the hit movie Knowing, or the Maze Runner series of novels or movies, or of course, one of the worst disaster movies ever made, 2012, you know that in the right writer's hands, the sun can destroy the Earth. In fact, this is so common that the website TV Tropes has given it its own name. It's called the solar flare disaster, where some outburst from the sun either destroys our entire planet or conveniently just destroys human life and leaves the rest of the planet intact. But I'm here to tell you that we don't have to worry about that. That's Hollywood. But the sun does have obviously direct consequences to our life on Earth. We kind of need it. We need its light and heat. So it's good to respect the sun and to respect the changes in the sun that occur over its evolutionary life, as well as from day to day. So here is sort of a cutaway cartoon showing you the different layers of the sun. We'll start from the inside, from the heart of the sun. That's sort of the business end. That's where all the light and heat come from. That is the thermonuclear core. That is where, thanks to Albert Einstein for letting us know that E equals mc squared, the sun is converting some of its mass into photons, into energy via light, every second of every day. Our sun has been converting hydrogen into helium for over 4.5 billion years in its core, and it will continue to do so for another 5 or 6 billion more years. Now, those photons, that light energy that is emitted in these thermonuclear reactions, bounces around in what we call the radiative zone, and then eventually reaches sort of the outer part of the inner sun below the surface. That's called the convective or convection zone. You probably know convection as boiling. Hot material rises and cooler material sinks. So nearer the surface of the sun, we have sort of a rolling boil of gas. bringing energy to the surface, which is then emitted as photons as the sun shining. So if we look out at the sun, which of course we should not do, that's part of my message today, is to be careful when you're looking at the sun to make sure you're doing it safely, you would see a whitish ball in the sky. That is the visible surface of the sun with scary air quotes, because the sun, being a ball of hot gas, does not have a solid surface, but that we can't see through that region, which is why we call it the surface. That's the photosphere, photo as in light. That is what the solar section of the AAVSO monitors, the photosphere, that visible surface of the sun. If you happen to have a hydrogen alpha filter, you can see the next layer up, the lower atmosphere of the sun, what we call the chromosphere. The chromosphere is a pinkish reddish layer, which gets its color from the hydrogen alpha line. And if you see a total solar eclipse, you can see the final layer of the sun, the crowning glory of the sun, the corona. So here is an actual photograph of the photosphere, and you can actually see what looks like bubbles that are boiling on the sun. This is what we call granulation. So the brighter areas are the hotter gas rising, the cooler is darker, and that's the material that's sinking. So again, with a hydrogen alpha filter, you can see the chromosphere. You can also see the chromosphere during a total solar eclipse. Again, during a total solar eclipse, most people are going ooh and ah around the corona. But if you look very carefully on this picture, you can see that thin pinkish red layer, and that is the chromosphere. And for those of you who have not yet seen a total solar eclipse, what are you waiting for? I've seen 5. I want to see 5 more before I die at least, right? So if you get an opportunity to see a total solar eclipse, take it. There's one coming up in April of 2024 that's crossing diagonally across North America. And I'm sure that a lot of people here, even if you don't live in North America, please come over here and watch it because it is well worth it. Now, the core of the sun is the hottest part of the sun. That is the only place hot enough to do thermonuclear fusion. But what's interesting about the outer layers of the sun is that as you move from the photosphere to the chromosphere to the corona, the temperature actually goes up as well, which is counterintuitive because you're farther away from the heat source inside the sun. The corona reaches about 2 million degrees. It is so hot that it emits a lot of ultraviolet and X-rays. I don't care what SPF sunscreen you have, you don't want to be blasted with the radiation from the corona. But again, what we see is the photosphere. And so looking at the photosphere in this mock-up cartoon here with the actual photograph above it, hopefully it's very obvious that there are these darker appearing regions, which are known as sunspots. Sunspots used to be called maculae. Those are darker appearing areas on the photosphere. And the reason why I brought up the term maculae, even though we don't use it very much anymore, is to contrast it with what we call faculae, not faculty. Faculae are brighter than faculty, believe me. Faculae are the brighter appearing regions on the sun. They're brighter appearing because they are hotter than the average of the photosphere, and the maculae, the sunspots, appear darker because they're cooler than the surrounding area. And so in this actual photograph, you can see both maculae and faculae. The faculae are harder to see than the sunspots. You normally only see them on the edge of the sun, which we call the limb, because you're looking through more gas when you look along the edge or the limb of the sun. And so there's more of a contrast between lighter and darker areas. So the sunspots are the most obvious of all solar activity. They've been monitored continuously since the time of Galileo, although we do know that ancient Chinese and other Asian astronomers saw them well before Galileo did. The sunspots, again, appear dark. They are not actually black. They appear dark because they're cooler than the surrounding area. If you could surgically remove a sunspot with a scalpel and hold it with some asbestos tongs, it would actually glow red like the dying ember of a fire. And the great thing about sunspots is that they're always changing. Some sunspots can exist for maybe a few hours. Some can last for several months. And even though they might look small to you, as you can see from this scale picture here, some sunspots are actually much larger than our entire planet. Now, it's been known for a long time that sunspots are a magnetic sort of activity on the sun. There are places where the local strength of the magnetic field is 10 to 40 times greater than average. For you uber geeks in the audience, we measure it by something called the Zeeman effect. If you look at a very well-developed area of sunspots, what we call a sunspot group, you will see that there is actually some substructure to it. If you are an eclipse aficionado, you might know the terms umbra and penumbra. Umbra meaning dark or shadow, penumbra meaning almost dark or almost shadow. So in a very large group of sunspots, you will notice that there will be a very dark appearing core, and then perhaps surrounding it, an area that's perhaps sort of grayish, not quite as dark. The darker is the umbra, the not so dark is the penumbra. So as I said, we have had almost continuous observations of sunspots going back to the 1600s, thanks to Galileo and other early telescopic viewers. And we actually have some of Galileo's beautiful sunspot drawings. And because they monitored them over time, it was noticed that day after day after day, the sunspots would appear to move along the surface of the sun. So there's only one of two choices. Either the sunspots are getting up and running across the sun, or the sun itself is rotating, carrying the sunspots with it. And it's actually the latter which is happening. Again, the sunspots, individual sunspots can live for as little as, an hour or so, or can live for several months. But not only are individual sunspots always changing, but the number of sunspots and sunspot groups on the sun is always changing as well. And so we call this the sunspot cycle. If you look at this data, which only shows the last few sunspot cycles, it goes up and down and up and down and up and down. Notice that not every peak is as peaky as some of them. But if you look at the spacing between the peaks, you notice that it's not perfectly regular, but sort of regular, quasi-regular. On average, there's about 11 years between maximum sunspot activity, but it can be as short as 7 or 8 years, and it can be as long as 17 or 18 years. What's interesting, and one of the reasons why the sun is considered a variable star, is that the sun varies in measured brightness by about 0.1% over the sunspot cycle. And interestingly, the sun is brighter at sunspot maximum. And I can show this to you. In the bottom graph, we have the sunspot numbers. These are monthly averages. And the top graph, and again, look at the scale, look at the y-axis. It's not changing by very much, but it's definitely going up and down. And the maximum periods of solar brightness correspond to maximums of sunspot activity. And that should strike you as being backwards, because remember that sunspots are darker appearing areas because they put out less light. So how could having more sunspots correspond to being brighter? The answer is, don't forget the faculae and the flares and other kinds of activity. Sunspots are just the most obvious kind of solar activity. There are many other kinds of solar activity that occur in the photosphere and the chromosphere and the corona, but they are all interrelated. So when there are more sunspots, there's also more, statistically, of this brighter activity, and the faculae and the other brighter activity more than compensate from the light you're losing from having more sunspots. So that is why for stars, this is not true for all stars, but for stars like our sun, when there's more spots, there's generally a tiny bit brighter, higher luminosity coming from the star. Now, if you look at a group of sunspots, you will often find that sunspots, they kind of have a buddy system. They have what we call a bipolar structure. I love these beautiful drawings that are much better than anything that I could do. And you can see very clearly that bipolar structure. And I've circled some bipolar groupings here on this actual NASA photograph. And over time, you can watch an individual sunspot group evolve. And there's actually names for all of these and code for all of these different sections of the evolutionary tree of sunspot groups. And again, this is all laid out in the AAVSO solar manual if you'd like to geek out on the evolution of sunspot groups. So that begs the question, why do sunspots normally come in bipolar groups? A key to understanding that is, again, to understand that these are magnetic phenomena. And if you look at the two main spots in a bipolar sunspot group, one has a north magnetic polarity, the other has a south magnetic polarity. And what happens is that at one of them, the flux lines go out of the sun and then come back in, sort of like an exit wound and an entrance wound. And what's happening is as these magnetic field lines are coming out of the photosphere and going back in, it actually blocks hot gas from rising to the surface. And that's what cools that area right around the sunspot. So sunspot activity is a key to understanding the transfer of heat in the exterior of the sun. Remember, I said that confusingly, the chromosphere and the corona are actually hotter than the surface of the sun. And sunspot activity also plays a role in that as well. Because again, at these bipolar groups, this is where the magnetic field lines come in and they loop around and go back in the sun. And what can happen is that these magnetic field lines can cross, they can deconnect and reconnect. And all of this transfers a tremendous amount of energy, which heats the outer layers of the sun. But for those of us that just like watching the sun, and I'm not going to be too concerned about the astrophysics about what's going on, watching the sun from day to day, as Galileo did, allows us to measure the rotation of the sun. It takes the sun about a month to spin once. So it actually will take a group of sunspots about 2 weeks to go from one limb of the sun to the other. But there's an interesting caveat to that. If you look at sunspots that are closer to the equator, they actually move around the sun faster than sunspots at higher latitudes. The sun has what we call differential rotation. It spins at different rates at different latitudes. And it's allowed to do this because it is not a solid body. It is a ball of gas. And what astrophysicists have figured out is that this differential rotation completely messes up the magnetic field. Now, the magnetic field popping up and coming back in is just part of what's going on here. You also have a twisting motion this way. And what happens is that the magnetic field gets so hopelessly twisted up after about 11 years that essentially the sun has to just cut its losses, snap, and start all over again. But when it does that, if you look at this diagram very carefully, you'll notice that the direction of the magnetic field lines is changing. The polarity of the magnetic field of the sun changes from one 11-year cycle to the next. So the way I sometimes describe this to my students is, if you imagine kittens playing with a ball of yarn and tangling up the yarn, sometimes you just can't untangle it. So you have to cut out the bad piece of yarn and just tie it back together and cut your losses. And this is essentially what the sun does. And this is what causes our sunspot cycle. So our sun is considered a rotational variable because as the sun rotates, we see different sunspots. But there's also a larger periodicity of about 11 years, again, of the sunspot cycle. So our sun sort of has two variability cycles, a short term and a long term. And there may even be longer periodicities in the sunspot cycle as well. So the question is, how normal is this? And the answer is, it's pretty normal. In fact, Gene Roddenberry, who you may know, late Gene Roddenberry, the creator of Star Trek, did a letter to the editor many, many years ago to Sky and Telescope, arguing that the star 40 Eridani should be considered the home world of Vulcan, primarily because it had a star spot cycle similar to our sun's. So when our sun sheds this magnetic field, it creates these huge bubbles of gas called coronal mass ejections. And these have direct consequences to our planet. Here, for example, is a beautiful picture from NASA where we've blocked out the photosphere, and we can just show you these huge magnetized bubbles of gas coming out of the sun. And sometimes they come in our direction. So there's a constant outrushing of high energy particles from the sun every second of every day called the solar wind. And the solar wind flows at about 300 miles per second, not miles an hour, miles per second. And our magnetic field generally protects us from the solar wind. Most of the particles just go around. The solar wind is part of the reason why comets have tails. But while most of those high energy particles go around us, it's not all of them. Some of them get trapped in what we call our radiation belts or the Van Allen belts. But some of them can actually sneak down closer to our atmosphere. Our defense system has sort of a gaping hole at the north and south magnetic poles. So when these high energy particles get into our atmosphere, you get a cascading effect of energy. Our atmosphere becomes energized, and we have what we call a geomagnetic storm. Now, perhaps the most famous and most beautiful of all the effects of a geomagnetic storm is, of course, the aurora borealis, the northern lights, and of course, there are southern lights as well, aurora australis. And the different colors are due to different elements as well as different heights in the atmosphere. Commonly, you'll see a green aurora that's fairly low altitude, but high altitude red emissions can be seen from much larger distances. So aurora that are seen farther away from the magnetic poles sometimes can tend to be red. And so if you see a red glowing light low in the sky, if you're not an astronomer and don't know what this is, you might mistake it for a fire. And there's a lot of mythology about red aurora being heavenly fires. And in fact, in World War II in California, when they had done blackouts because of the war, there was actually a red auroral display, and people thought that the Hollywood Hills were on fire, and it was actually just an aurora. But there are some things that aren't quite so pleasant when we have one of these geomagnetic events. It can actually overload transformers, leading to blackouts. It can pose radiation danger to spacewalking astronauts. It can fry the electronics of satellites. It can disrupt radio communications. This is one reason why the American Radio Relay League, or ARRL, keeps an eye on solar activity so that these ham radio operators can make adjustments in their signal when they know that the sun has energized our atmosphere and affected their radio broadcasts. If the sun is more active than average over a long period of time, it can have a cumulative effect, and it can energize, give energy to the molecules in our atmosphere, and it can actually cause our atmosphere to puff out a bit. Now, I know all these rich billionaires are arguing about who's really gone into space and who hasn't, but if you're looking at where the definition of space is, one way to think about that is it causing drag on your satellites and making your satellites spiral in towards the Earth? This is Skylab. I actually have a piece of Skylab here. Skylab was the first American space station, and it actually was a victim of a higher than normal period of solar activity. Its orbit decayed sooner than expected. Don't worry, the astronauts were long gone. Much of it burned up over Australia, but some pieces have indeed been recollected. But this can also be the fate of other satellites orbiting the Earth as well. So hopefully you see that solar activity is really a problem of technology, of how it can impact our technology. And one great example of that is the so-called Carrington event. Astronomer Richard Carrington in 1859 saw a rare white light flare. I've only seen one of these in my life in many, many years of solar observing. They're pretty cool. And about 17 hours later, there was a huge geomagnetic storm registered on the Earth. Aurora were seen as far south as the Caribbean. People in New England could read newspapers at night by the Aurora. Back then, the chief technology of communication was telegraph. Telegraph systems failed, and telegraph operators actually got electric shocks from the metallic equipment. So if it could have done that in the 1800s, what could a Carrington event do to our technology today? That's what people are concerned about. That's why people are interested in solar activity. As sort of a prelude, in 1989, there was a huge geomagnetic storm which caused a blackout, which took out the grid of not the city of Quebec, the province of Quebec. Again, Aurora seen as far south as the Florida Keys, Cancun, Mexico. You had apparently California Highway Patrol and Minnesota broadcast on the same frequency, which is normally not a problem. But when radio signals are bouncing off the atmosphere in abnormal ways, they were picking up each other's signals, and garage doors were opening and closing as if they were haunted by themselves. So solar activity is a problem for human technology, and it's estimated that a Carrington type event today would cost the US trillions of dollars, just the United States. So we are now going into solar cycle number 25. What will this look like? And will my cell phone signal be safe? Well, they've been trying to look into their scientific crystal ball and try to estimate what the next solar cycle is going to be like. But again, if this is solar cycle 25, that means that we've only officially scientifically measured 24 before that. That sample size is a little small given the natural variations in the sunspot cycle. But this means that it's a perfect time for you to get on the ground floor to start observing solar activity. It's predicted to peak in July 2025, but again, we don't know exactly when that will be. It could be a year and a half earlier. It could be a year and a half or more later. What we do know is that if you look, and this is from spaceweather.com, back in 2020, 57% of the days of that year had no sunspots. This year, it's only been 18% of the days have had no sunspots. And we're pretty close to the end of the year. So the sun is definitely waking up. And in fact, this beautiful picture from the astronomy picture of the day from September 9th, 2021 shows a huge smattering of sunspots, much more than you would expect for this early in the solar cycle. So this solar cycle is, at least so far, is a bit of an overachiever. Here in red is what they expected, and the actual data shows that the sun has been overachieving on what was predicted. Now, to look at the sun safely, you are not going to just use your eyeball. Again, we're not going to be staring at the sun with just our eye. You can see very large sunspot groups, the size of Jupiter or so, with your eye if you use something safe. In other words, if you use eclipse glasses that you might have had from the last total solar eclipse. And as I said, we have historical sunspot records going back pre-telescopic. Here we have a medieval manuscript which has sunspots, and we also have, again, Chinese and other Asian cultures, and also we have Maya, pre-telescopic Maya records as well of sunspot activity. So when we look at the sun, we are looking for areas of activity. An area of activity is called a group. A group might have one spot. It might be an isolated area of activity with one spot, or it could have 20 spots. So we're not just counting the number of spots. We're also looking for centers of activity. And this is where experience comes in. Because to monitor the sunspot activity, we define something called the Wolf number. The Wolf number gives a statistical weight to the areas of activity. So we take the total number of spots, S, we take the total number of groups, we multiply the total number of groups by 10, and then add the total number of spots, which means that the Wolf number jumps from 0 to 11, because if there's one spot on the entire sun, the Wolf number is 10 times 1, which is 10, plus 1, which is 11. So who was Wolf? Rudolph Wolf was at the Zurich Observatory. He was the standard observer, which made this methodology very nice because you have a standard observer using standard equipment. After he retired, he was succeeded by Wolfer. And after Wolfer's time, we have continued to use the same methodology, but because we are not using a single observer, we have to put in a reduction coefficient so we can compare apples to oranges, if you will, or Granny Smith apples to other kinds of apples. So the solar section of the AAVSO has been observing the sun for decades. Here is a picture of our website with our quick links. You can get all sorts of information about observing the sun here. A quick history. It was started by necessity in World War II. World War II disrupted the flow of solar observations from the Zurich Observatory. And again, because solar activity affects radio communication, it was a matter of national security for the US to have access to reliable sunspot and solar observations. So Leon Campbell suggested that an AAVSO solar section be formed. It was adopted formally in October of 1944, and by mid-1945 had 53 dedicated members. And so our prime function is to produce the sunspot counts for the National Bureau of Standards for the American Relative Sunspot Number. We have the AAVSO Observing Guide, which is currently been translated into 6 other languages other than English. If you are interested in translating into other languages, we would certainly be happy to talk to you about that. Let me give you a brief introduction to how one does this. There are 2 different versions. There is projection, and there is what we call a filter. There are about 70 observers worldwide who provide counts every month to the AAVSO solar section, about evenly split between the 2 methodologies. So projection is exactly what the method states. You are not looking through your telescope. You are projecting the image onto a screen. This is safer for your eyes because you're not looking through the telescope. However, it does put stress on your telescope because the full brunt of the sun's energy is passing through your telescope. So do not do this method if you have a compound catadioptric telescope. Also, you don't want to use your expensive compound eyepieces to do this as well. To see as much contrast as possible, you want to keep your projection screen in the shade, which is why you'll notice there's sort of this collar here on the telescope. And to be safe, you want to remove or cover your finder scope and keep all body parts out of the light path. A filter removes ultraviolet, infrared, and visible light. It is safer for your telescope because you're preventing the light from entering the telescope to begin with. Again, you want to remove or cover the finder scope. So this is bad. You want to make sure that the filter fits snugly over the aperture. It has to be on the front of the telescope to prevent the light from entering in the first place. Back in the 70s, there were some cheap refractors that were sold with eyepiece filters that were supposedly to look at the sun. Some of them failed. Some people lost eyesight. A solar filter goes on the front of the telescope and prevents the light from entering in the first place. And you must check your filter every single time for any imperfections. I have a solar filter right here that I use. You see that it looks like a mirror, blocks almost all the light going through it. To check it, you visually inspect it for any imperfections, and then you go outside and you hold it up to the sun and you move it around and you make sure that you don't see any bright areas. And then once you've ascertained that your filter is in good working condition, then you put it snugly on your telescope. So here I have some pictures with some no-nos here. So if you'll notice the picture on the left, this finder scope doesn't look like it's covered. And I would actually remove it. I've removed the finder from my telescope because one time I was doing an eclipse observation and I had the finder scope covered and somebody tried to uncover it. So I removed the finder scope, okay? In the picture with the projection, I don't like the fact that her hands are a little close to the image. Now, at the point where the image is, it should be safe. But if she moved her fingers closer into the eye, towards the eyepiece, it could be quite dangerous. So keep your body parts out of the line of fire of the sun if you're using projection. Which begs the question, if you take your finder scope off, how are you going to line up the telescope? You do it by minimizing the shadow. Because your telescope barrel is round, or if you really fancy and you have one of those like octagonal or hexagonal ones, if you minimize the shadow of your scope, you can actually line it up with the sun without looking through it. And you can also buy some devices that will help you line it up as well, but this is free. So the disclaimer is you are responsible for your own safety for solar observing. I'm not responsible. The AAVSO is not responsible. The solar section and the manufacturer of your equipment are not responsible. Please check your equipment before each observation and do so without distraction. If you want to send in your observations to the AAVSO, we have software called Sun Entry. You will put in your AAVSO observer code username and password, and it's very easy to use. You just put in what the month is, the day, the time, the seeing conditions, the number of groups, the number of spots. It automatically calculates the Wolf number for you, and if you have any remarks, you can put them in, like, for example, if the edge of the sun was particularly turbulent that day. And you can actually check the database for your observations. So you can see how it sort of spit out some of my observations. And also notice that not every month am I putting in a lot. I mean, here was 1 month, I only put in 1 observation. Every observation is important. Don't be concerned that you can't observe 25 days out of a month. Any observations are valuable. So every month we take the observations and we put them in the solar bulletin, which has the statistics of the aggregates of your observations and has other information about solar observing. You can get all of the past solar bulletins online through the website of the solar section. And how do you improve as an observer? Well, what I did was when I first started, this is one of my early observations, I was overcounting groups. So I would deconstruct my observations every month. I'd go back and see what I was doing wrong. And that's how I got to be a better observer. So a lot of it really is just experience. You can also ask for a mentor through the AAVSO mentor program. So I'd like to invite you all to come to the, I don't know if we are the dark side, I guess we're the light side. And I don't know if we have cookies, but I will tell you that we have a whole lot of fun. So be one of the proud, be one of the solar observers. Thank you very much.
Thank you so much, Dr. Larsen. That was excellent. I see we've got several questions here, so let's go ahead and get started with the Q&A. First question comes from Adam Nowak, who asked, what about calcium K filters? And do we observe the chromosphere or the photosphere of the sun using those?
Well, calcium, the H and K lines, those are strong calcium lines, as they said. Frank, are you familiar? I know Frank's here. Frank, are you familiar with K filters? I don't use K filters. I know that they can be used, I believe, for chromospheric activity. Thinking back to the professional, like for example, when we're looking at spectra of sun-like stars. Has Frank chimed in the chat?
Not yet.
Okay. But so the short answer is the AAVSO does not collect observations in that bandwidth. We actually are not even doing hydrogen alpha. We are strictly doing these white light observations.
Thank you. And let's see. So Frank has just chimed in and he says, I do not use calcium. So okay. Next question. This one comes from an anonymous attendee who asks, at the beginning of your talk, when you had said something about 200 nuclear weapons, which kind of nuclear weapon are you comparing that solar flare to? Because they range from 10 tons of TNT yield to 58 million tons yield.
I believe typically they usually compare them to Hiroshima bombs.
Okay.
But at this point, the fact is, big boom.
True. Thank you. Jay Lavender has a comment. He says that he can confirm that the calcium K line in the calcium K filters reveal the chromosphere.
Thank you.
Okay, and we have a comment here about using a Herschel wedge. Jay Miller says that if you have a refractor of 100 millimeters or less aperture, you can use a Herschel wedge. Do you have anything to add to that?
We're not really recommending. There's been a lot of back and forth about Herschel wedges. We're not really recommending those. If done correctly, Herschel wedges can be safely done. If done correctly. So we prefer to use the ones that are simpler and have perhaps a larger margin of safety here. So
that makes sense.
Yeah.
Thank you. Okay. Now Jeffrey Kassoff has asked, how much hotter than the photosphere are the flares?
The flare, let's see. The corona is, and again, I'm doing this all in Kelvin here. The photosphere is like 6,000 Kelvin, and the corona is in the neighborhood of 1.5 million Kelvin. And so the flares are in, in that general ballparkish order of magnitude sort of thing.
Okay, thank you.
Yep.
Thank you. All right. And another question here was, you had mentioned earlier that you gave us an example that you could put in the notes for an observation that the edge of the sun was more turbulent than usual. Are you referring to a physical effect of the sun's edge appearing blurry, or is that an effect of the seeing?
Excellent question. A really great example was the observation I just did today. We're having a cold front coming through, so it's incredibly windy out. So the air is incredibly turbulent. And so if there are any sunspots right on the edge of the sun, and because of the seeing conditions, the edge of the sun is very turbulent, you can miss those. And so that's why for today's observation, I made a note that the limb of the sun was very turbulent. And that's basically the seeing conditions. I mean, the sun looked like it looks like a jellyfish today. It was really bad. It's really windy out. So yeah. But again, it's all what you're trying, and some of the other comments I've put in sometimes is if there's been a thin haze. So perhaps there might have been some small spots I might have missed. So anything that you think, if it's a matter of trying to figure out whether your observation that particular day is trustworthy or not, or whether you think you might have missed something, put in that little comment. Put in that comment.
Interesting. Thank you. And another question on the topic of seeing was, what is the best time of day to make an observation?
Early in the morning. Everything's a trade-off. Okay, so you want the sun to be high enough in the sky so that you're not looking through more air. All right, but the longer in the day that you wait, the more the ground heats. So the more you have air currents coming up from the ground. So the answer would be in the morning, not so early that the sun is incredibly low, but in the morning-ish. And technically, if you want to do the best job possible, look out over grass. Don't look out over black asphalt. That tends to have more of that air currents, the mirage effect. So when they redid our observing platform outside, I'm in my office right now on the roof of the building, and the observatory is actually above my head. But we have an observing platform out here, and the really nice people wanted to paint the ground black on my observing platform, and I had a cow, and I said no, I'm not doing solar observing on a black asphalt painted observing platform. So they painted it light gray, so I'm happy now.
Great. Okay. This next question comes from Timothy Weaver, who asks, what about using a DSLR to take pictures as a means of adding an extra factor of safety alongside the solar filter?
You can certainly do all sorts of wonderful photography. Obviously, when you're using any sort of aid, you want to make sure that you are keeping your eyes safe and your equipment safe. So, putting your camera up full blast onto a telescope, projecting it rather than no, you don't want to. But there are people who take excellent filtered pictures with DSLR, and you can actually buy and you can actually make filters for binoculars, which are great for eclipses. The AAVSO, because we have this historical continuity over many decades, we are trying to keep our way of doing observations consistent since the 1940s. That is why your observations need to be done in a particular way so that we can compare them to what's been done. And so we have a consistent record. So DSLR is not consistent because it's not what we were doing in the 1940s. So while it is a wonderful and valuable thing to do, those are not the observations that are being uploaded into the AAVSO. It's like if you do the regular variable star, you have a lot of choices, right? You can do visual observations, you can do DSLR, you can do photometry, you can do CCD. And you have to say which one you're doing, right? Because they're comparing those to each other. For the solar, we only have visual. We have this one way that we do it. And to keep our data valuable and consistent, we are keeping with that with that one methodology. And every once in a while, we look at it. Remember, I said that because we don't have just a single observer, we have to put a sort of weight factor in front of the 10G plus S because we're comparing different observers to each other. Every once in a while, we relook at that. We relook at our statistics and make sure that there isn't any creep in the statistics that might be getting it out of whack, so that we can compare historically going back over decades. And that's what keeps our database valuable and relevant.
Great answer. Thank you. All right, we're almost out of time for questions here, so I'm going to say we'll take 2 more questions, and then after that, if you want to continue answering questions, you're welcome to do so in written format in the Q&A box. So first of our remaining 2 comes from Dipankar Day. Apologies for mispronouncing your name, I'm sure I did. Who asks, why are there more sunspots in the equatorial region than the polar regions?
Well, technically, you will not get sunspots exactly along the equator. And you do not get sunspots up in the very high latitudes. You get them more in the so-called temperate regions. And it depends upon where you are in the solar cycle. At the beginning of the solar cycle, the spots will tend to start at higher latitudes. And later in the cycle, as the sun's magnetic field has gotten all twisted around, the sunspots tend to be seen closer to, but not exactly at the equator. So it's a symptom of the differential rotation and the tangling up the magnetic field. It creates something called the butterfly diagram, if they want to go Google the butterfly diagram.
Okay, thank you. And last question for now. Groups of sunspots may be easy to see, but counting spots can be hard when they are small. Even a 60mm refractor can be hard to use to see small spots. Do you have a recommendation about how to best detect spots with a 50 to 70mm refractor? Any eyepiece recommendations or that sort of thing?
It is tough. I will say that use any of the methodologies that you use to try to see faint fuzzy objects while you're observing. For example, if you jiggle the telescope a little bit, if there's something there, you'll see it move. And then once you know it's there, then you can say, okay, I know I saw something out of the corner of my eye in that part of the sun, and let me see if I can see it now. So any of those little tips that you use to try to find faint fuzzies at night, to try to trick your eye into seeing things, go ahead and try to use those when you solar observe as well.
Thank you. That's good advice. So that's all the time we have for questions right now. But Dr. Larsen, if you would like to, you're welcome to continue answering questions in written format. You're not obligated to, but you're welcome to. Thank you for an excellent presentation. Okay, and Dr. Larsen, also, if you could go ahead and end your screen share real quick. There you go. Thank you. All right, so on to our next speaker. If you attended our last webinar, you might remember when Dr. John Thorstensen mentioned an amateur astronomer from Poland who has been doing some very impressive work and making an enormous amount of new discoveries. Well, ladies and gentlemen, I am most pleased to announce that with us today, we have none other than Gabriel Murawski, the amateur extraordinaire himself. As a dentist during the day and an astronomer at night, he began his search for new variable stars in 2017. As of today, he's discovered over 3,000 of them, all recorded in the MGAB catalog. Today, he will be teaching us all about the MGAB project, its history, its methods, and its most interesting stars. So, without further ado, please allow me to introduce Mr. Gabriel Murawski.
Thank you a lot, Lauren. So good evening, everyone, or good afternoon, depending on which time zone are you currently in. Let me prepare the screen share. Okay, here it is. So, slideshow from the beginning, yes. So, today we'll talk about the MGAB variable star catalog. This is the largest project I have done so far about astronomy. this is a very long topic, so I will try to talk in a brief as much as possible because this presentation can take many hours. So I will not focus on some basic stuff. For example, what is this variable star about? But I want to focus what exactly have I done in the last 4 years. So to begin with, I will start with my history. My interest about astronomy was 15 years ago, as far I remember. Just 2 years later, when I was just 12 years old, I observed my first variable stars. It were visual observations. I remember it was Bipolar or Delta Cephei. It took a few years until I got a scholarship that allowed me to buy my first camera. It was Canon 60D that allowed to me try photometry for the first time. The results were very promising because the photometry allows to get better precision. So I decided to go a little further with this subject, and 3 years later, I bought my first CMOS camera. It was Altair camera based on EMX224 sensor. And after that, I bought a few more cameras, and this latest one with me, AC1600 in MM Pro, is the camera I use for this type of observations. The beginning of my journey about variable star discoveries, the catalog here, started in 2017 when the Universe Exoplanet Explorers project has started. You all probably heard about Planet Hunters project that appeared around 10 years ago, as far as I remember. This was the second project. It was focused not on the first stage of Kepler telescope mission, but the K2. I was very amazed about how many stars are that variable that you can detect with your equipment. So after classifying a lot of light curves, I decided to try something further into that subject. I selected a few targets that at that time remained unknown, and with that, I performed some follow-up observations, and I discovered my first variable stars. It was some data mining and my own observations. So this was a little bit complex, not at the typical discovery that you observe a random place in the sky and you suddenly see something. It was the third observation because when I observed Qatar 5b, I noticed there's something interesting about one star that is nearby. This is the light curve on the right. This is the eclipse of this variable star named right here. So this was my third observation. I was very amazed because it looked like nowadays you can still discover something. It didn't take a lot of time after the first two discoveries. It was around 2 or 3 weeks. And it turned out that my second interest, not only discovering variable stars, but also exoplanet transit observations, I noticed that there are really a lot of stars you can still discover. After more than 50 discoveries, I found something untypical that started my another project. It was the beginning of data mining. Soon after that, I was looking for more ways how you can discover a variable star without observing. So this was just the data mining method. And soon after that, a few of my friends joined the search with me. Mariusz Bayer, Adam Derdzikowski, Krzysztof Kida, or Adam Nowak, who is with us right here. With us, there's also Miłosz Puszyński, who also recently joined the search. And we in Poland try to find something really interesting. We are all amateurs and we try to do something for astronomy from amateur side. After discovering some rather common variable stars, I decided to go a little further. How can I discover something more untypical? So I started looking at catalogs. The first one was Rosat's X-ray sources, which allowed to find some rotating variables, flaring variables, sometimes even complex ones. For example, an eclipsing binary with some star spots on them. Then I came back a little further. I started to look at objects showing infrared XS. If you ever looked at all-wise images, you will see that stars are usually blue or green right here. Some are red. These are young objects, and this allowed me to find more untypical objects, and this allowed me to see that you can also find objects of interest based on colors. So later I moved to Gaia DR2, the data release 2, from which I discovered my first cataclysmic variable. And just a few weeks, or that was months later, ZTF and PanStars released their first data that allows finally to go a little deeper in magnitude, not what ACSSN allowed, that was around 17 magnitude, but down to 20 or 21 magnitude. And as a finish, because there were really a lot of variables, more than I could actually submit to variable star index, I started multi-object searching by cross-matching many catalogs, and this at this time I opened my website where I submit my recently found objects, and then they are submitted to variable star index. That allowed to speed up the process a little faster. And that was my, so far, best way to find really interesting objects. In short, how I did it. I said before, I was looking for objects based on colors, based on properties from existing catalogs. So, for example, let's say we want to find some Mira stars. We know there are these Mira stars have high indexes, so the BP minus RP magnitudes from Gaia should have high values. So I ran the ADQL query on Gaia to get a list of such objects. Then I cross-matched the list that's around 1 million or more objects that show the highest indexes. And then I cross-match with ZTFs, maximum and minimum magnitude values, to find which of them show the highest amplitudes of variability. Then, after I select the top objects, that's usually a few hundreds, a few thousands, maybe more, I download light curves of these objects, and then I start analyzing them. Here, what you see is a screenshot from Excel, how the Universe project from my side looked like. So I can see light curve of my candidates, variable star candidates, and if I am focused on only a specific type of objects, for example, RCB, that you can see right here, I can really speed up the process quite fast. The problem is nowadays, is the variable star already known or maybe not yet? Honestly, I'm really focused on only objects that are truly unknown, because when you find something that is yours, you can really focus only on it, because when someone finds a specific variable star, okay, that's your project, you focus on it. I have my own set of variable stars, so the thing is it known or unknown is very important for me. So that's why I take a look at all possible catalogs to make sure that these are indeed discoveries, and I will avoid being sad after some weeks or months that my submitted variable star was already known. So that would mean maybe some waste of time. So I tried to avoid it. So that what I have said about finding variable stars was the first stage. The second stage is to revise all variable stars I have submitted so far. One of things that I am focused at are get more data from ZTF, because nowadays we have ZTF DR8, for example, or also pan-stars. With latest data, we can get more precise amplitudes, variable star types, or even positions, because nowadays we have Gaia E DR3, not DR2 I have used before. And after some time, I found more catalogs of variable stars. So actually the amount of my submissions, not 3,776, but there's a little less. My job about my work about second stage is still not finished, but I think it will end around 3,600 variable stars that are actually discovered by me, not mentioned as a variable star, as a confirmed variable star before. There's a thing why I don't continue the first stage. So why I moved on. The first thing is Larsen. Larsen is a website that is working on ZTF data, but the problem here is all stars that have been observed by ZTF are analyzed all the time. That means whatever star you try to find on this website, it would say they have already analyzed it because probably there's some artificial intelligence working on it all the time. So the thing is what I will submit, is it actually something known or maybe unknown? I don't know how to treat the website, so I don't want the problem that I was talking before. Something that is really unknown is an important thing for me. The second thing was the problem about the variable star catalog of candidates from ZTF DR1. The thing is, this catalog contains a lot of objects, but the access to that catalog was very problematic. I couldn't get to it, so I wasn't sure if what I will submit, is it actually also unknown? Because I know after some time this catalog will be available to public. It will appear in Visor, for example, so that will be much easier to handle. And the problem, another thing is, actually I've submitted way too much variable stars that it really takes a lot of time to analyze all of them. My second stage started in the beginning of this year, and I still have a lot of to do. Now about what you can find in this catalog. My search was mostly focused on cataclysmic variable stars. That's the most important project. Also HW Virginis stars, so Hub subdwarfs with red dwarfs orbiting these stars and showing eclipses, and eclipsing white stars that I'm working with Sigrid van Orbeke, and maybe he is here with us. If not, we will for sure he will watch my webinar later. Here what you see is a small table of variable star types that are submitted to variable star index. Not all stars are here because I have analyzed all stars except the latest set of 2000 variable stars that contains Mira stars, semi-regular variable stars, young stellar objects, and some other variable types. Actually, these stars are not my main interest. It was actually about the number, to be honest, to find out how much can you actually submit, as how much can you do as an emitter. So later, my analysis was focused only on the previous sets, exactly cataclysmic variable stars that we will talk right now. So here what you see is the amount of up to date from ZTF DR7, now ZTF DR8, variable star types of all cataclysmic variable stars I have submitted so far. Eugeneran variable stars are the most common one. There's almost 600 of them. And because the ZTF has very precise light curves, I was able to say a little more about these stars. What exactly types are those? Now we'll talk about the most interesting discoveries from my side, from my importance. And I will try to tell why are they actually interesting and what further follow-up. The first variable star here is MGAB V859. It is the first variable that is actually a hybrid of Ursa Majoris, Ursa Majoris and Z Camelopardalis variable star types. It is the first actually known. Soon after that, the Professor Taiji Kato found another similar star from the ZTF, and there were two such cases already known. But from my recent analysis, MGAB 702-8 shown the same thing. So we actually know only 3 such cases for now. Why is it important? The rareness of these types. The usual variable star type, we know about 40 or maybe 50 only such cases, and in my catalog there are about 25 there was in that list. I don't remember exactly, but these two stars are actually untypical because there's something more about them. We see standstills. The moment when there are no outbursts observed, right here and right here, if you see my cursor, of course. The next type of stars, the nova-like variable stars showing an eclipsing companion, is type of stars that were actually less known before. There were only a few such cases known a few years ago, and my work allowed to find about 20 more such cases, which allowed to find more targets. Actually, it's in all cases in variable star types, more such variable stars that are properly classified, because everything what is done here is not automatic, it is everything manual. Every light curve you see right here is not what any program did. This is all my work manual in Excel that took my recent months, sometimes 7 years. This is actually something I did this year, because the second stage, the revision, is currently taking place. The first variable star that is cataclysmic variable star was not actually this one, but the first variable star was just how can I say, quite a surprise because I wasn't looking exactly at categorizing variable stars. It was just in the list, and I see, wow, there's something interesting, untypical happening about it. I thought that it was a dwarf nova, but it turned out to be a polar. But the reality about categorizing variable stars was in the beginning of 2019, when I submitted the first novel-like VI sculpture is variable. That is actually my one of favorite types. It reminds me of RCB variables, but it's not a red object, but a blue object, a cataclysmic variable stars. RCBs are red. That's completely different objects, but light curves look quite similar at first glance. And the first, and actually first two variable stars of this type are quite bright. So it's quite, some people even say it is quite surprising that we haven't known there as variable stars before. It was noticed that late in 2019, while such objects were already this brightness of this type of stars, mostly around 10 or maybe even 20 years ago. And one of these stars was made us a little surprise. I said I was very interested about this type of stars, the VA sculpture is novel-like variable stars, because I noticed that these stars in variable star index are often showing the NA type. I mean, some of these stars show some classical nova eruption in the past. So I decided to submit all these stars I can find with hope that maybe one day in my life, one of them will erupt as a classical nova. And the surprise is it took just a few months, not actually 1 year and 7 months until this thing that has happened. MGAB V207 actually erupted as a classical nova in constellation Reticulum, and it turned out to be a really bright object. It was visible for naked eye for about 2 weeks, maybe even more. I don't remember how exactly. And it looks like that something I have discovered might be something actually worth looking at the future, because all these VA sculpture stars are definitely worth watching in the future, because something like this might happen again. This nova eruption was first noticed by Robert M.C. Naut, and here in the right you can see the picture taken by Ernesto Gaido, Marco Rocchetto, and Adriano Valvasori. The next stars, the MGAB 249 and 69, were also something new for nowadays science. At the beginning, these stars were completely unknown. Variability about these stars weren't confirmed anywhere. It turned out to be something really new, something we have never seen before, something that shows clearly an eclipsing binary, but the period was quite too short to be a V Ursa Majoris variable or beta Lyrae type variable, because the period is about 1 hour or even less. For the case in the left side, the period of that is just 39 minutes. So at the beginning, I just submitted it as interacting binary variable stars, interacting white dwarfs binary type of variable stars. And I was waiting what else can I do with that? I found something actually new, so I emailed Riviera Sandoval. She is an astronomer that I am collaborating with. And she looked at it and said, that's something interesting. Let's try a look if it shows some X-ray and ultraviolet emission. And soon after that, I received an email from her that there's a paper currently about to be submitted by Thomas Kapfer. So I contacted with Thomas, and after some talk, I was added into the paper named the first ultra-compact lobe film COP subdwarf binary, and I became a co-author of these variable stars you see right here. So because they looked at these stars also earlier, I was the first to publish, not the first to find, but the first to submit. So this, what we have here, are independent discoveries with Thomas Kapfer and all people that are involved in the paper. Another project that I really enjoyed, not from now from categorizing variable stars, are eclipsing white dwarfs. When I began the search of these objects, there were only a little amount of objects known. The process of finding these variable stars is quite untypical because I'm not looking here at magnitude errors, so from catalogs. I needed a list of, if possible, all white dwarfs I can find in catalogs. From this set, I cross-matched with ZTF, and I started looking at variable stars that show high difference between maximum and minimum magnitude, but the average magnitude or the mean magnitude should be around maximum. That means the variable star shows small variations, but there are some measurements that are actually much below than usual, than normal. And in this plot you see right here, it is actually happening. I only needed to find the right period to find the gap that is caused by an eclipsing companion around a white dwarf. And so far I have found 57 such stars. This is a really small group, so it's quite easy to find in the internet for the full list. So actually 57 stars are actually unknown that I have already submitted in 2019 and in recent year. And not in all cases I was able to determine the period. I'm pretty sure that the missing 12 objects are actually eclipsing white dwarfs, but I need more data, so I'm waiting for more data coming from ZTF, so I can finally find the right period. To find it, I need to observe them myself, but unfortunately these objects are fainter than 19 magnitude, so it's a little too faint to my 8-inch telescope. So instead, I'm waiting for more ZTF observations, and I need at least 7 eclipses to start finding the gap. If there are less, I probably will find more possible periods, and that's still not enough to say what type of eclipsing object there might be. These stars are really quite fun in our analyzing because you can actually get a lot of information about them just by seeing at colors and from the plot and from the period as well. Because some variable stars of this type show reflection effect. Sometimes it's visible, sometimes it's not. In this case, you see right here, it's quite flat. The size of the eclipse can be wide or maybe a little narrow. That says a little more about the size of the object. Not exactly the exact size, because we have also the inclination. So if the angle is a little smaller, the eclipse will be also a little narrower. And also from infrared access, you can find if it's actually a definite red dwarf or maybe something having a little less emission, most likely even a brown dwarf. That was found in 12 cases. These are not definite brown dwarfs yet, because we need radial velocity of these stars to confirm it. We haven't done it so far yet, but there's one star named MGAB V1134. We found it as an almost definite brown dwarf orbiting a white dwarf. Why? Because the period is so short, 104 minutes, that the period is so short that the density of the companion must be a little higher than usual, than typical for stars, to be actually stable. That shows that at this short period, a red dwarf is rather unlikely. And I want to thank Secret, Van Verbeeke, Saul Rappaport, and Andrew Vanderburg for help in all this analysis, for performing these observations with the NOT telescope that shown what exactly we have right here. Now we are going a little backwards, because the MGAB V165 was the first submitted variable star that is actually quite important. All stars I have submitted earlier were actually common variable stars. This was finally something untypical, because the XOR variable stars are, we know really less, we know really a small amount of objects of this type, about 60 as far as I remember, and this one is actually the 14th brightest XOR currently reported so far. And I'm pretty sure there are more in the set, but they are hidden in that 2000 that set of 2000 variable stars that I still have to finish. And another variable star that is really fun in observing too is the MGAB 266. This is an HW Virginis type binary that consists of a hot subdwarf and a red dwarf. These stars orbit around every 5 and almost 6 hours. So the period is really short, but the very interesting thing about this is that eclipses here are actually total. So far, we have known only one such example, and this was the second such object known. And what's important, this one is much more brighter, because in maximum it's at around 15 magnitude, and the amplitude is so large that you can see on this animation right here from my own observations, that for 20 minutes the star can completely disappear. And the fact it is bright and the amplitude is so large, the light curve is it's so detailed that allows to measure the eclipse, the moment of eclipse, so precise, up to a few seconds. And this is enough for my small telescope. Is it large or small, 8 inch? You can do a lot of things with that. even with stars, untypical stars that I was able to find, it allowed to start to measure the time of eclipses. Why is it important? Because in many bright cases of HW Virginis variable stars, that there's also a tertiary body orbiting these stars. So maybe it's a chance to find maybe your own exoplanet too. And this star is very important for my work because this is what I have already observed with my friends. Based on data from ZTF about 1 year ago, maybe it's already a little earlier, I have noticed that the measurements from 2020 are also off to those that were from 1 year earlier and 2 years earlier. And nowadays it is continued. We are performing a lot of observations. So thank you, Adam Popovich and Tony Van Monster for observations of this star. Also to other people, Adam Novak, who observed it a few times, to Mariusz Kalisz, a person who is working on YouTube on Astrolife page, who has shown this to a lot of people during a live stream. He took his camera and a telescope and pointed exactly at this target to show other people at the eclipse it is showing. So thank you a lot. And we are moving to another variable that looks like important from in my opinion. The next one is 282. This is an eclipsing binary that is in an eccentric orbit, but there's actually something important happening because there we have also the heartbeat variability too. And what makes this variable unusual is the amplitude. Because so far the highest record was this one you have in front of you, and this one shows eclipses that are much deeper. That makes it actually a new record. And what's more, there's actually a third companion because the Northern Sky Variability Survey data has shown that the secondary eclipse compared to the primary eclipse was a little moved. That means that we have apsidal motion here too. And another one of the recent variables that I have submitted. This is a young stellar object that has an eclipsing companion. But the thing is, these eclipses are quite untypical because it's not a typical U or V type shape of eclipse, but it's a little complex. This what we have here means that there's something more than just a second star. Is it actually a new young object? Because for sure, this is actually a very young object because this shows infrared excess in 2 mass and WAIS data. But in this case, we are clearly seeing that the companion shows something too. Maybe it's a proper protoplanetary disk, or maybe even an exoplanet showing rings. The second one is less likely because we have here the secondary eclipse too. But what is interesting, a few years earlier, the SSSN data shown that it wasn't even visible. So there's a lot of dynamic stuff going right here. And we are almost finishing. I want to add that my work was is about discovering new variable stars, but I'm working on exoplanet transits too. So far, I have submitted some observations of TESS candidates, and they are still waiting until they are published, and we are waiting for that. So far, with help with many projects, with help with LianQ and many others listed below here, and the WWVSH project, they allowed me to co-discover, not a typical co-discover, but a co-discover 5 new exoplanets where one system is multiplanetary. And what will be next? The first thing, with latest data, I have noticed that many nova-like VI sculptures variable stars were actually polars. So that means we need more data to be sure, is it this type of stars or maybe this? Second, a lot of huge enduring stars listed are here show typical behavior, typical outbursts that are saying they are most likely to be ZCAM variable star type 2. So with more data, our classifications will be more precise. Not all objects from cataclysmic variable stars are certain. That means in some cases, I don't really know what it exactly is, because I still haven't found from papers from known variable stars what is it exactly. So with more data, I will be able to determine what exactly it is, because there are more than 20 such variable stars that are really worth further follow-up to make sure what are these. And the classical nova stars is what I have already said before. Yes, I am planning to observe with my own equipment as much as possible these stars, the VI sculptures variables, from the catalog in search. Maybe we will have another eruption, maybe again. A lot of variable stars show, from the cataclysmic, of course, show an eclipsing companion, but it's not visible at first glance. Sometimes you need really more data to see that there's actually something additional. With more data, we can maybe observe. With more data, we can have our properties of the second object orbiting the white dwarf to make it more certain, more precise. So this is what I want to do with these stars in the future. The SU Ursae Majoris variable stars. The thing is, the classification in the variable star index changed, and nowadays you need to observe superhams to make sure this is exactly this variable. And because there's more than 100 objects waiting for the confirmation, that means these stars are certainly worth further monitoring to make sure, is it exactly this star or maybe not. Eclipse timing variations, it's what I have explained before. Quasi-periodic eclipses around young star objects. It's like that binary showing complex eclipses just before this slide. And what I'm also doing, except the second stage, that means the classification again, the revision, is to look for papers to make sure is any of variable stars I have submitted before appeared in any paper, because some people, and I want to thank to all these people who involved me in their papers for mentioning me that I have found, I have analyzed this exact star that appears in this catalog. Unfortunately, not everybody does that. I have noticed around 50% of papers that include variable stars from this catalog actually mention about work I have done so far. So this is mostly because in not all cases people look at variable star index, so it is also my able to take a look at this database tool. So so in that way, the discovery credit can be correctly given. I am looking at this very importantly. When I notice that my variable was submitted somewhere earlier, yes, I will change the who actually discovered it, but actually not everybody is going this way. And the last stage is, of course, it would be a very good idea to publish this as a paper. In this case, I will not be forgotten because as a paper, people will know, yes, there's an exact paper, we can cite it, and there's no problem. But the thing is, there's a lot of variable stars in this catalog. I'm doing this for more than 1 year, the revision process, and after looking at it, I'm in a little lost situation because honestly, there's so many variable stars, more data appear all the time. So that means it's worth reclassifying, doing recheck of already revised variable stars. And this actually never ends. Hopefully I can do it soon. And thank you everyone for attending to my presentations. And now I can answer any questions if you have.
All right, thank you so much, Mr. Murawski. Let's take a look at the questions. All right, our first question coming from Moises Lohmiller, and this is, I'm sure, what everyone's wondering. If you work as a dentist during the day and you observe at night, when do you get your sleep and your rest?
Okay, so the thing is, it will be a little easier in near future because when I started my studies about dentistry, I graduated almost 1 year ago and a few months. I was able to observe only in 3 months, in July, August, and September. That means there's only a short time when I can actually observe anything with my own equipment. So, because the data mining became the main project in my variable star work, it meant I could start doing from computer, and I didn't need to use my equipment to observe some variable stars, and I could do it every time, so it wasn't a problem. And now, after I graduated, I am working too. I will be moving to a new house, and finally, I will be able to set up my static observatory and start observing more. So that means it was never a problem. You can do variable star stuff also during the day, and this what you do on daily basis isn't a problem.
All right, thank you. That's a good point. Our next question comes from Francis Hempsch. Apologies for mispronouncing your name. I need to learn how to pronounce it someday. Who asks, could you please give a link to where to find your catalog?
In one of slides right here, I will paste it. Let me find it. Okay, so it's right here. I will post it in the chat. Where is it? Q&A. Oh no, type answer right here and send. Okay, so in this page, you can see all variable stars, almost all variable stars I have submitted with updated light curves. Not all of them, but this website is still going, this derivation is still going, but every single star that is in the catalog, you should find exactly here. You can also use variable star index to find these stars, but not everything is updated yet because I want to finish everything from this side first before I can move to variable star index. I want to make sure that all my classifications, all my checks on the discover credit, everything from this side is finished before I can move to variable star index. But also, yes, in variable star index, you can find every MGAB star too.
Great, thanks. That makes sense, wanting to get all the data in order before adding it to VSX, so thank you. And next question here is about what are the different ways, if there are any, that AVSO observers could help with characterizing these stars?
Okay, the thing, stars, variable stars, these stars that are worth further monitoring are certainly this showing eclipse time variances. I would say these stars, I think, are the most important because this is what happening, what we have around these two stars, because we have a tertiary body. It is orbiting mostly at a period of many years. That means we need to observe eclipses all the time, if possible, of course, all the time to find the exact time and get the OC graphs that will help to get a precise model of what we have already right here. This is pretty sure the stars that need the most attention. From other stars, I'm pretty sure these ones, these cataclysmic variable stars that looks like they show an eclipsing companion, but I was still unable to find the right period because sometimes there's too less data or the scatter was too high. That didn't allow me to find the exact period, so it's still yet to be found. That's what I'm actually also planning by observing, but this will happen after a few months before my new setup is ready that I have mentioned before.
Okay, thank you. And on the topic of your website and AVSO observers helping out, we have another question here that Franz Joseph Hemsch asks, could you give a list of the most important stars in the Southern Hemisphere up to magnitude 17 or so that he should be monitoring?
Yes, I will prepare the list, but unfortunately, almost all variable stars I have submitted are actually in the Northern Hemisphere. But because there are some targets that are actually quite low with declination about -10 or -20 degrees, there are still quite less measurements from ZTF. That means many of these stars, some are eclipsing white dwarfs, some are other types, they are still yet to be observed to finally find out what exactly we have right here. Not only that we just have an information that there's just an eclipsing white dwarf, but maybe we can characterize it a little better. So yes, I will prepare the list for you. I have already an email, so that's not a problem. We'll talk later. So we'll keep in touch, and pretty sure we can collaborate about that.
Wonderful, thank you. And last question on that topic is about your site for the MGAB catalog. Is there some sort of a priority list on that site or perhaps elsewhere online that anyone here in the audience could access?
The priority list of targets, the most important targets that are worth monitoring. I would say actually these stars that need further monitoring and monitoring that observing that cannot be finished by doing it just right now. This eclipsing time variations. This needs observing for many, many years to finally be sure what exactly we have right here. And about lists, this is also what is planned after the revision. In my website, I want to prepare lists of exact variable star types, stars that need monitoring, that have high priority, everything that is actually in many cases answers to many questions. For example, I am interested in these stars. What have you in this catalog? I have prepared the list. Here's the link. You can take a look. So that will be done also soon.
Thank you. Sounds like a good goal. And let's see. Looks like the last question we have here, unless nope, no questions on Facebook. Okay, our last question is
Yes.
Do you have a favorite star out of the many that you've discovered?
My favorite star is certainly the MGAB V266. That one showing eclipsing time variations. I really like this star to observe because when you take your telescope, take your camera, you can observe the eclipse in your screen. That is happening very, very fast. You just point your telescope at this target, you see your star, and you just wait a few minutes until it completely disappears. This is something that we can actually observe almost we can observe anywhere, because the second target, actually we know three, there are two in this catalog, but these other two are much fainter. This is actually quite bright to observe without any problem in front of your screen. You don't need to use long exposure time. You don't need to stack. You just open the software of your camera and look how your star completely disappears, and after 20 minutes reappears again.
All right, thank you. Wonderful. That star is definitely going on my list. All right, we have a comment on that question real quick before we finish things up here from Adam Nowak, who says that a similar object in terms of brightness and ability to observe is MGAB V287, but that one has almost instant eclipses.
This one is also worth observing. This star is co-discovered with me, Adam Nowak, and Mariusz Bayer too. But in this case, we don't have a hot subdwarf, but a white dwarf. It's a little fainter, but we still can see how dramatic eclipse it is. Because the white dwarf is tiny, the large red dwarf can eclipse it almost instantly. The eclipse from the beginning and from totality takes just seconds, less than a minute. That means with our data, with our camera, we can see that the star can completely disappear in one frame. But the little problem about this is the eclipse is a little longer. I think it's 40 minutes right here. So you need to wait a little more time to see how it reappears. And we have two nearby stars that makes it a little quite difficult to see. But if you have a really large scope and a color camera, unfortunately, I have a mono camera right here, you can also see how the color of this star changes. Because white dwarf looks not rather white, but rather blue in these frames. When the total eclipse happens, we only see the large red dwarf that is faint. If you have enough aperture, you get enough magnitude limit on your frames, you can see that red dwarf that is red. The color is completely changed during the eclipse. And this is also what Mateusz Kalisz has shown today to his viewers in his live streams on Astrolife YouTube channel.
Cool. All right. Thank you. And that's good to know about MGAB V287 for anyone who missed the designation of either of those. Adam Novak has kindly put them into the chat, so feel free to write that down, add it to your observing list. Okay, and it looks like that was the last of our questions. So I'm going to go ahead and put up our closing slide here. Thank you so much, Mr. Murawski, for an excellent presentation.
Thank you a lot. Thank you a lot, everyone, for coming too.
There we go. All right. To close out this webinar, I would like to extend a huge thank you to both Dr. Larsen and Mr. Murawski for sharing their time and knowledge with us today. I would also like to thank again our sponsors, DC3 Dreams and Voice Astro. DC3 Dreams provides high-end observatory automation and web-based multi-user remote imaging. The AAVSO net observatories use DC3 Dreams ACP Expert for the Bright Star monitors and other programs. The AAVSO Photometric All Sky Survey project, also known as APAS, has used ACP Expert's AI scheduler to automatically acquire over 500,000 star fields, hands-off, at a rate of 1,000 square degrees per night. This has resulted in photometry for over 128 million objects in about 99% of the sky. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Okay, with that out of the way, I have some good news for everyone, which is that today's webinar has been recorded. Right this very second, you can find it on our Facebook page, and before too long, it will be uploaded to our YouTube channel, where it will join an ever-growing library of educational videos just like this one. After 2 successful years of webinars, we have covered a lot of great topics, so I do highly recommend that you go check out our YouTube channel. And if you like what you see there, can't imagine that you wouldn't, please do consider subscribing to our channel. It only takes a single click and you will help us increase our educational reach. That one click will make YouTube more likely to suggest our videos to others. That's one way that you can help support the AAVSO. And another way that you could help support the AAVSO, if you're not already a member, join the AAVSO. AAVSO membership is a great bang for the buck. We have a wide array of membership benefits, including access to our mentorship program. So if you're interested in starting to do some sunspot counts like Dr. Larsen was talking about, we do have mentors who can help you with making sure that you're doing things correctly and safely. And we also have a stellar remote telescope network. We have some pretty impressive scopes in the network that I wasn't aware of until just recently. And now I want to shout to the world that we've got some meter class scopes you guys could be using. Just sign up for the AAVSO. And as always, we would be extremely grateful if you'd consider donating to the AAVSO. Every single donation matters and goes towards making programs like this one come to life.